Everyone can see my screen.
Yep. Yep.
Sweet. So yeah, this is a. Oh, go on.
Go on.
Okay. So yeah, this is a project that I've been doing the drafting for. I joined maybe like halfway through, and helped out with the drafting, and then I've ended up taking over most of it, and it's pretty much finished now. There's just a few like loose ends that we're tying up, but I've not done any engineering.
Yep.
But I went through some of the engineering design yesterday just to see what they actually did in terms of designing for acoustic.
Okay.
So I just went through and had a look at a few different examples. So the project's basically two buildings, 6 floors of apartments, and then 2 basement levels, which are car parks.
Yep.
Design and construct. And then the engineering scope is mainly just like heat loads and ventilation.
Okay. So the rest of the design is being done by the contractor, is it?
I believe so, yeah.
Okay.
I'm not actually too sure because, like I said, I didn't really do any of the engineering stuff, but from what I can see. So yeah, I just picked out a few examples. So they're mainly like fan acoustics. So I went through and just had a look at some of the different examples. So this one here is like a basement level in the car park. It's an outside air fan. And I just had a look at the mechanical spec, like what they wanted, what we ended up scheduling. And after a quick read through the document you sent through, Peter, I had a look at this table in the Australian Standard 2107.
Okay, yeah.
So just thought it was a bit interesting to see the different ratings that, kind of the standard, what they ask for. So for a car park, the maximum was 65 decibels.
Yep.
What they asked for initially in the spec was actually a little bit, I was around that, but a little bit higher, which I thought was interesting. And then we ended up
there's sound power levels as well.
Right.
So hang on, I'll request control so I can point at things.
Yeah, sure.
As we go through. So these figures here are sound power levels, and these figures here are sound pressure levels. Right. So there's quite a difference. Equipment noise is usually expressed in sound power levels, and for us to do calculations for acoustics, they have to be in sound power levels. That's the starting point. And we'll go through some calculations when we talk about acoustics a bit.
Yeah.
But so these are sound pressure levels, and dBA is they use the dBA, the A weighting, because that most closely represents what we hear. So we hear sound pressure, sound power, we can't hear it, but it's there. It's like an invisible power in the air that is being converted to sound as it transmits. Anyway, just carry on.
So what you're saying there is you'd have to convert that to make it comparable. You can't just compare the two values.
Yes, yeah, they have to do the calculation to determine what the required sound of the fan would need to be. But anyway, look, it's usually when you select a fan, you'll get the sound power levels, and see the selection you've got here. It's 47. That's 47 dBA. That's it.
Okay.
That's the sound pressure level. So they give you the sound power level so you can do the calculations if you need to, and they'll give you a sound pressure level. So, which is an A-weighted overall sound level, it's obviously not a spectrum, it's just an overall level, which is when you combine all the values in the spectrum to get the what's called the overall sound pressure level. So 47 dBA, and you're trying to achieve less than 65 dBA, so you really don't have too much to worry about there.
Yeah. Okay.
A small fan in a car park like that's not going to cause any issues.
No.
The only issue might be if there's noise coming out of this louver, and you've got a neighbour nearby, or the building itself, if there's say a residential apartment very close by,
Yeah.
that may be an issue. But 47 dBA again, I don't think would be a problem. It's when you're getting up into the 60s, 70s, 80s, that you're going to have issues.
Yeah. Go to the next example.
I just noticed there, sorry, on that one, for the benefit of others if they're not aware, you've got fast clamps on that fan.
Yeah.
So is everyone aware of those? For those small cylindrical fans, the fast clamps have got a rubber insert which enables you to not only connect the fan to the circular ductwork, but it also gives you some vibration isolation in the rubber. So they're very useful for those small circular fans. Okay.
Yeah, that was one of the first ones I'd pick out. And then there's another fan here. This is a roof fan in the form of a roof cowl. Similar thing, just went through this table from the Australian standard, compared with our schedule and the mechanical spec. But the interesting thing about this one is that the part of it has to be insulated. And I remember when I was drafting this, one of them wasn't and one of them was. I didn't really understand why. But it's because obviously this one here isn't an actual fan. The fan is at the bottom. So I guess any noise coming from that would have been dealt with in the basement.
Okay.
Whereas this one obviously needs to be dealt with. I think it's like a meter or two.
You've got a branch there at the at that level. Is it that's the top level, is it? So that's providing fresh air to the apartments, is it?
To the corridor, yeah.
Oh, corridor. Okay. Yep. Okay. So they're trying to attenuate some of that noise before it comes out this first branch. And that one is 56 dBA. And in the corridor, you're probably looking for, you've got it there, have you? What's this?
Yeah, common areas. I don't know if that counts as a common area, the corridor.
Oh, I suppose it is, yeah. It's a bit small. Oh, yeah, okay, so 55 dBA. Okay, so the fan's 56, so yeah, a little bit of attenuation there is a good idea, just to make sure that you're not creating a noise problem in the corridor.
So how would you know if that's enough? So I think typically we use 50 mil insulation and duct. And then if the fan's rated at 56 and it says the maximum there you can have is 55, how would you know that that would be enough to reduce it before it gets to the corridor?
The only way you can be absolutely sure is to do a calculation.
Right.
And when we talk more about acoustics, I'll point out an acoustic calculation sheet that's available. It's in the Fantech data, the Fantech fan selection program.
Yeah.
That's also got an acoustic calculation program.
Right.
And you can use that. I don't know whether Phil and Ivan have any other spreadsheets that you can use for acoustic calcs, but they'd probably point you to the Fantech one. It's quite easy to use.
I've got an example. I can pull up an example. I've just pulled up it now. If I can take over.
Yeah.
Just quickly.
acoustics is a very big topic, and it's going to take you some time to really come to grips with it. But having a basic knowledge and an awareness is important. I'll give you an example. When I was managing quite a large engineering group, probably 10, 15 years ago, I decided that the whole team could do an acoustics training program. So we got a specialist to come in, an acoustic consultant, and he brought in notes for everyone, which was about a ream of paper of how to go about doing the acoustic design for a project. And it was over the top. But anyway, he spent, I can't remember how long, but several days with us in a group trying to teach us the basics. So that gives you some idea of how much is involved. But really, if we can do the calculation, we understand what we're trying to do, it's not really that hard once you understand the basics. Anyway, go on, Jess.
Yeah, interesting. Yeah, so I just pulled up that same fan model at the airflow and static pressure.
Yeah.
So then at the top here, you can see there's acoustic analysis. If you click on that, I'm a bit rusty, so I'm going to remind myself how to do this at the same time.
Yeah.
But yeah,
so
basically,
it starts with the sound power levels.
Yeah, yeah, exactly. So you can specify whether that's at the inlet or the outlet of the fan. In this case, it's inlet because of the type of fan it is.
Well, actually, hang on a sec. If you're analysing the noise downstream of the fan, you probably need to look at the outlet.
Yeah, but this is a suction. It would be at the inlet in this case, right? Because it's roof mounted. Is it supply or exhaust?
It's supply fan. It's outside air supply.
Yeah, right. So then you would do outlet then.
So it's probably not much different, but there may be a difference of 1 dB or something like that. So
yeah.
And just while we're talking about this, when you do the no, look, keep going. I won't confuse it. Keep going.
All right.
I was going to mention something about attenuators, but we're not at that stage yet.
Yeah. So then, basically, then you select the right one, inlet or outlet, and then you work your way down this list. So first, if you've got ductwork connected to the fan, you can model, kind of crudely how much attenuation you get. So it's rectangular duct. What's the dimensions of the duct, Jordan, in that?
500 by 500.
Riser. Okay. And roughly how long is that run?
About 2 meters.
2 meters. Okay. And let's just leave it as unlined for the moment. You can see it takes 1 dB off at each of these frequency sort of bands, and then it doesn't really do anything with the higher frequency sound.
While you're on that, just click on the line and see what difference it makes.
Oh yeah. So was it 50 mil?
Yeah.
So you can see it makes a big difference. So it is quite effective to have that lining adjacent to the fan.
Yeah, especially at these higher frequencies. This is more like the audible range, like 1K sort of.
So I'll just say what I was going to say before now. The one that's the most nuisance in a building are the low frequencies, particularly 125 and 250. And so you're getting the lowest attenuation there because they're low frequencies. The sound has a high wavelength at the lower frequencies. You understand the relationship between wavelength and frequency. So it's always the most difficult to attenuate low frequency sound. And the low frequency sound is like a drumming sound, which you'll get from a fan. So just be aware of that as well. And I do mention that in the notes I sent you. So we'll talk about that some more later.
Yeah. Then you can if you've got a square bend at the bottom of that riser, you can also model that. So with turning vanes or without turning vanes. I'm not sure what you have, but you can put in width, the number of. So square bends also attenuate quite a lot.
Yeah.
A little bit less of the low frequencies, but still help.
Yeah.
And then depending on your outlet area, like the larger that your outlet area is, I believe like then the air velocity will be lower. So then you get more attenuation. So, sometimes you'll see like a transition at the end, like a kind of bell on the end of the duct, which brings the velocity down when the air is supplied into the space. So you can model
Yeah, it's
what your outlet area
basically
is.
the neck size of the grill. Okay, so if you've got say a 600 by 600 diffuser in the ceiling, the neck size might be somewhere between 300 square and 450 square or something. So whatever that neck size is, you put that in there. So you can put something in there, just so it's a 300 square neck, which is 0.1 of a square meter.
Yep.
So again, so you're getting good response at low frequency there, which is good.
Yep, and then if you make that, like say, bigger, you get a bit less attenuation.
Yeah.
So it's actually the opposite to why does it go that way? How come with a smaller outlet area you get more attenuation?
Because it's related to end reflection. I'll try and explain this in basic terms. It's when the air is passing down the duct and it comes to an outlet where it's going to actually leave the duct, there's actually a resistance of the air to leave the duct. So there's end reflection. So the smaller that is, the more resistance there is for the noise to come out. So it's hard to explain, but if you can imagine, you can look at the physics of this, but there's a sound wave passing down a duct and it comes to the end and it's got to find its way out. And some of the noise will come out and some will be reflected back, even though it's an open end. So it's just called end reflection and it's a fact.
So more end reflection means you have less sound entering the space.
Correct, yeah.
So you actually want that, yeah.
And also be aware that, and we'll talk about this a bit later as well, but on a supply air system, you generally have a lot more outlets than you do on a return air ductwork system. And the sound power is distributed to all the outlets. It doesn't just go to one, it's distributed through the whole system. So you're losing power at each outlet, which is important to realise when you're looking at selecting attenuators, that the supply air attenuator, if we need them, will generally be smaller than a return air attenuator. Because on the return air side, you need more attenuation because you might only have one opening in that system. Like one return air grill compared with, say, 6 or however many supply air grills.
So if you're trying to do this modeling, say, with multiple outlets, then do you include the duct losses and square bands for all of the outlets, or is there like an index run, so to speak, for the acoustics?
It basically is an index run, yeah. And generally, it's going to be the closest to the fan.
So you'd only do this modeling for that one because
Yes.
most of the sound will escape from that path.
Yeah. Well, not most of the sound, but the sound will continue to attenuate the further you go down a duct system. Okay, so if you attenuate the first outlet sufficiently, then the rest of the system will be fine. Does that make sense? So you're always looking at the closest outlet to the fan is what we need to concentrate on to attenuate the fan noise.
But that doesn't guarantee, though, that for the next closest run, like the next closest outlet will be sufficiently attenuated, will it? Like you could put a lot of lining on the closest one, and then if you put nothing on the next closest one, and it was still pretty close, then that might not be sufficient.
Well, the lining you're going to put on the duct, there's no point lining any ductwork after the first outlet. if you're lining it for acoustic attenuation, up to the first outlet is all you're going to do, because if your first outlet is satisfied, then the rest of the system will be okay as well. So that's why if you've got, well, like in this example, you've got a fan, it's lined down to the first bend, and then we're looking at the sound from the first outlet at the highest level. Similarly, with a fan coil unit, you might line or you normally do line the return air plenum and the first, or the transition from the fan coil unit on the supply side, and maybe the first piece of duct. And then after that, there's no value acoustically in internal insulation. That makes sense? Look, it's very difficult to describe, and to describe it technically, you have to go back into all the physics of it all, but that's, from a practical sense, that's how it works. There's no value in internal insulation for acoustics after the first outlet.
Yeah.
But you might choose to internally line all the duct anyway, because it's more convenient, and it doesn't really cost that much more to do that. And I think we've talked about that before, that when do you internally line ductwork? If it's a small job, you might as well internally line the whole lot, because then it can be done in the factory, and you don't need another contractor coming to site to apply insulation.
Yeah. Yeah, no, that makes sense. We have talked about that. All right. So anyway, you can also just add any additional attenuation at specific frequency bands if you want.
What's the drop-down box for that, please? Yes. What's in that? What are the options there? Nothing. Oh, I can
just do, yeah.
Whatever you want to add. Okay.
So is it at that point you'd have like a acoustic engineer? If you're still worried about your acoustics in the system and you've done all you could do, the additional attenuation amplification, that would be something that would be studied by an acoustic engineer, right? Because we don't know the extent of the options after that, right?
Yeah.
This is very crude at the end of the day.
There is another spreadsheet, which is, if you go to...
I'll just finish going through this.
Yeah.
And then we can go on. There's just a few more things to do. So then once you're done with that, you're happy, you click OK. And you can see already the sound pressure has come down from what it was.
Yeah. So just go back. You've got sound power level at the top here. Sound power leaving the system, direct sound pressure. So between the sound power leaving the system and direct sound pressure, there's correction factors. To convert from sound power level to sound pressure level, there's a spectrum of correction factors which aren't shown there.
Yeah.
But they are shown on the other spreadsheet. But anyway, keep going.
So
isn't it there at the bottom? It says the sound pressure. There's dBA and it has a list of them. Is that because that was going to be my question. Is that what you would compare to that standard?
Yes. This
pressure,
is like the final. Yeah, exactly.
Okay. So that, okay, it says 42. So you can say, if you're selecting an attenuator, the line that says required dBA, you can put a number in there, and you're talking about 55 dBA as the max, weren't you?
Yeah.
So if you put that in there, required dBA, select a silencer. So what that's saying is you don't need a silencer, I think. That's all it's telling you.
Yep, if you pushed it lower.
Yeah, so as you go, now when it's the green ones mean that you don't need any attenuation, but the black ones are saying at 250 hertz you need some attenuation if you want to achieve 40 dBA. So go lower again, just as an example. If you're going directly into an apartment, 30 dBA is pretty low, but a hotel room, I've worked on hotels where they want 30 dBA, which is, so that people can have the air conditioning running at night and they can sleep without any background noise at all. And you can see there that you need more attenuation than we've got in this system. In crude terms, does that make sense?
Yeah.
And
Yeah.
and hotel rooms, in the bulk of the work that we do, we probably do a lot of hotel rooms or apartments where sound can be an issue. Probably not so much in apartments because people live there and they get used to the noise, but hotels, people come in and they want quiet, they want silence in their room. And they're very small rooms, it's just one room that they're in. So it can be quite difficult to achieve very low sound levels in a hotel. And if you ever do a sound studio, I did one once that was, I think it was 20 dBA. So, we had lots and lots of attenuation in the ductwork, and you've got to pay special attention to your fan selections and all of that. So, but that's fairly rare to do a job like that. But hotels are not rare, and apartments are quite common. So,
Yep.
just,
Yeah, I'll just keep going. So the next one that you do is the direct sound. So direct sound to terminal is like what percentage of the sound is coming via that terminal that you're considering. That's my understanding of it. Like if you got multiple terminals, then like Peter said, the sound will be spread, throughout them.
yeah. So if you put in there 50%, so you've got two outlets, so you've got 50%. So you're getting some attenuation because the sound is being distributed, sound power is distributed between more than one terminal.
Yeah. I'm not sure then how this couples to the duct system effects, like if you just put in the shortest path duct here, or if you put in the entire system, that's where it becomes a bit fuzzy for me.
Yeah, well, it is the shortest path.
Okay.
Yeah.
I
don't understand all the ins and outs of this program. You probably, if you could find the notes on it, which are probably available, you could work through that. But anyway, for the purposes of what we do, it usually works quite well.
Yeah. Okay. Anyway, then distance listener to terminal, we usually have 3 meters is usually what's in the tech in the data that you get from a fan tech selection. It's usually the attenuation at 3 meters.
Well, basically, I believe what that means is the air is coming out, or the sound is coming out at ceiling level, say, and how high is the ceiling? Normally, they might be 2.7 meters. How high is a person? Let's say 1.7. So it's about a meter. It's really how far is the sound source from your ear?
Yeah, so I don't know why then, like in all the schedules, it's always at 3 meters. Like typically that's what, like I'm thinking Jordan's schedule that he showed, it's always like sound
They say
pressure.
dBA at 3 meters.
Yeah.
Yeah, so that's the fan. Okay.
Yeah, right. But probably actually in this case you would put something more realistic, like is listener to terminal. So it's probably like, 1.5 or 2 meters or 1 meter. I did this for like a car park which had a huge, like a 9 meter high ceiling because it was a shed. So, I put in 7 meters and that, gets you so much attenuation. But let's say it's just 1 meter.
Well, in
Even
this
1
case,
meter.
it depends on the building. If it's a warehouse, it'll be the same. It might be 7 or 8 meters.
Yeah. Then you can select the terminal area, so I don't know, 0.1 up to 0.1 square meters, and the position in the room. Also, it gets you different amount of different contribution to the attenuation. If in the center of the room, you kind of get the least attenuation, I guess. Oh, hang on, this is actually not attenuation. This is adding. This is adding, isn't it?
Yeah.
Because wouldn't being next to the surface help attenuate? Like, wouldn't it make the sound dampen?
I think
Or
it's
is it
the
the
opposite
opposite?
here. So in the corner, you're adding like nine across the whole spectrum, whereas in the center of the room, you're adding like less than that. It could be that, I don't know, turbulence or something.
I guess sound
Um,
travels easier through solid, doesn't it, than it does through air?
It's
Yeah.
also about reflection. Like if it's in a corner, you're getting reflection off the corner bouncing off the walls. If it's in the center of the room, I would think in the center of the room would be the best position because the sound can disperse without being bounced around too much.
Right. Makes
But
sense.
it just depends on where it is. The grill is where it is to suit the project. So
Yeah. And then there's reverberant sound, which is kind of a feature of the specific room. Like if you've got a room that's, I don't know, bare concrete floor and minimal furniture, then it's going to be, quite echoey.
yeah,
So let's say that 100% of the sound is going into that area. If it's a dead room, so if it's a live room, that's what I'm talking about. Like it's very
yeah.
echoey.
So
And if
this
it's
is
dead,
reverberation where the sound is building up. It's like being in a room with a lot of people where the noise, if the more people are in there, the noise level just builds up and up and up. And that's because of the reverberation in the room. If it's like in a restaurant, for instance, if you go to a restaurant that's got concrete floor, hard ceiling, hard walls, it's very noisy and it's very hard to have a conversation with anyone. If you go into a room that's got soft furnishings, carpet on the floor, things on the walls, it's usually a lot quieter.
yeah. So yeah, just by having, like I say, what's called a dead room, which is soft floors and sound absorbing, things all over, you get quite a bit of attenuation at the high frequencies from that. You can also select the volume of the room. So yeah, that makes a big difference to the attenuation as well.
What other options did you have there in that absorption?
Dead, medium dead, like average room, office type environment, medium live, and live.
What would you say a corridor would be?
Carpeted?
A corridor.
Is
Oh,
it
it is
carpeted?
carpeted, yeah. I think that's it, yeah.
It's
Yeah.
probably average.
Yeah.
Yeah.
So you're getting attenuation because there's carpet on the floor.
So is that what you would take? So because you obviously there's no like thing to quantify it. It's just kind of up to you, isn't it? It's like your assumption. You're like, well, if there's carpet
Well,
on it, like what kind of thing do you go through in your head to say that this would be a dead room or this would be a live room?
They probably give examples here, I would guess, in this help, maybe, but yeah, I don't know.
There you go, absorption.
Here you go.
Okay.
Live
Okay.
room. Rooms with heavy hard surfaces and without any acoustic treatment, like factories, plant rooms, swimming pools, gyms. Calculations being based on all surfaces being concrete. Well, obviously, that's not going to be realistic for a corridor.
No.
Medium live room with hard, slightly vibrating surfaces, bathrooms, kitchens, schoolrooms, hospitals, based on plasterboard walls, ceilings with a linoleum floor. That's getting a bit closer. Then average, appreciable soft furnishings, e.g. carpet, offices, libraries, homes, hotel rooms, lecture halls. Calculation based on medium carpet floors with plasterboard walls and ceilings. So yeah, that's probably what you'd go with.
Yeah.
And then dead is like specially treated rooms. So you need to be able to justify choosing that, I suppose.
Yeah. Anything higher than like the average room, I guess,
Yeah,
that's specialist equipment.
Yeah, they're saying like your recording studios, thick carpet floors, rock wool lined walls, and a good acoustic ceiling. So yeah, probably go with the average here.
Yep.
And then if you need an attenuator, based on what your requirement is. So all of what we've just done is to do with the actual design of the space. But if you have a special requirement, which can be NCC or it can be, whatever what the client wants, then you can put in that and you can be able to select a silencer to achieve that. And then pretty much, yeah, you can select a silencer. Never done that bit. Oh, how do I get back?
Go back to acoustic analysis, I guess.
Oh, yeah. Yep.
So in this case, we're talking about 55. So you've put in some figures there that are fairly relevant to this, what we're doing. So if you put in 55 as the required dBA, it's saying that you need attenuation at 250 hertz of 2 dB, but
it's also saying we've achieved 49 here.
49 dBA, yeah, okay. So this is, I guess this is what I was saying before about the low frequency noises can be an issue. They're very hard to attenuate because of the long wavelengths of the sound. But if it's telling you that basically you might have a bit of an issue at 250 hertz in a corridor, I wouldn't worry about that, because the corridor is a transient space. The important part of this project would be the apartments themselves, that you're not creating a noise problem in the apartments, and you'll get attenuation between the corridor and the apartments. Even if the low frequency noise is a bit high in the corridor, it's not really going to affect the apartment because you've got heavy walls and a heavy door that the sound has to get through. And the best way to attenuate low frequency noise is with those sort of elements. Mass, it's got to go through mass, and it won't. So, well, it will to a certain extent, but that will attenuate it.
Yeah.
That makes sense.
Yep.
I'm not an acoustic specialist, don't get me wrong, but I have had a lot of experience over the years, and it is a big topic, and this is why I'm probably harping about it a bit, to be aware of it, and always to have a good look at it, because I mean, you get to a stage where you say, no, we don't need to worry about this system, that fan's going to be fine. Then some you might be thinking, oh, it might be a bit borderline, perhaps we should do a calculation, or perhaps we just put in some internal lining after the fan, which has been done. I'd say in your case, Jordan, they probably didn't do a calculation. They probably thought, oh, we'll just put some internal lining in the ductwork here and that should do it.
Yeah.
I'll give you an example that just comes to mind. I worked on a project on the Gold Coast a long time ago where they build boats, or big luxury boats. I'm trying to think of the name. It's quite a well-known manufacturer of these sort of boats, but where they were producing the molds for the boats, the fiberglass molds, we had to put some ventilation into that factory area. So it was a factory. It was all metal roof, metal walls, concrete floor, lots of hard surfaces inside because it's fiberglass molds, and no real attenuation. And we put the supply fans in. No, they were exhaust fans. We had evaporative cooling for supply and axial fans above the roof for exhaust. And because it's a factory and it's a sort of noisy place, we didn't put any attenuation in to start with. We didn't think we needed it. And when we started the fans up, got it all running, we had a noise level in the space of about 70 dBA. So it was too noisy. It was kind of just, you could say maybe borderline, but for someone to be working in that space all day at 70 dBA, it was too noisy. So all we did, we had the exhaust ducts ran horizontally and then vertically, and the fan was just above the roof. And all we did was put internal insulation in the vertical riser so that the sound coming in the horizontal parts and then up towards the fan, we had attenuation where it was, where we could get it in the vertical riser of the duct, and it was only about, say, 2 meters long, and that brought the sound down a lot. So that's all we needed to do, and we did that quite easily. I mean, we should have done it in the first place, but the decision was made not to worry about it, but it was an issue. So It doesn't take much with internal insulation to take the edge off the noise.
Mm.
So you do develop a bit of a feel for it over time, but there is the facility to do the calculation if you need to.
Yeah. I'll just share one quick example where I used this on a project. It was that car park, which was like an old shed, and we were putting an exhaust fan on the roof, and the like sort of for I guess like a value engineering thing, we chose a fan that was cheaper than the one that the consultant selected in order to save the client's money, but it was a little bit noisier. It was like 2 dBA above the maximum allowed noise level that's in the NCC. So we just came in here, and there was like a bit of duct, connecting to the fan coming through the roof, and we just found like with 1 meter of duct with 50 mil lining, it was enough attenuation even without bends to get below the within the standard allowance. So yeah, then based on that, we justified selecting that fan.
Yep.
But yeah, you wouldn't really do like a proper hardcore acoustic analysis with this. It's more just just to get an idea when you've got a fan, say, somewhere, and then you've got a room that's maybe very live or not so live, and then you can just see what the sound will roughly be doing through that system.
So it gives you a level of comfort that your design is going to be okay, because you won't know until the systems are commissioned, and if there's a noise problem, you think, oh, what do we do now? So if you think about it during the design process and make the provision to attenuate the noise if you need to, then you shouldn't have any worries at the end.
So if I share my screen again, I'll show you 2 examples where the acoustic analysis needs to be done. It's still waiting for it, actually. So in these situations, I can explain a little bit more. We can even go into like the drawing itself to get a bit more detail about them. But this one on the left is in the basement, and it's taking air from outside into the car park. So why is this needed to go to an acoustic engineer? Why was it not solved and designed based off of like, I don't know, like a fan tech, using the fan tech program?
So you're saying that they got an acoustic consultant to tell you what to do with this, to select the attenuators, or?
Well, this is just like the preliminary design, and then the fans. So the areas in these 2, so one's on the roof, one's in the basement. They're on hold at the moment because they need acoustic analysis. So I'm guessing the engineering team that worked on this weren't confident that there would be.
Okay, so
meeting the
who
specification.
made that note? Was that the contractor or was that us?
That was us.
Right. Yeah. Okay. Well, I'll tell you a couple of things straight off the cuff. The way, if they're thinking, can I request control again?
Yeah.
Now, this is quite important. So they're anticipating that an attenuator is required here. This is some sort of grate, is it, that lets the air come through?
Yeah, that's to outside.
And that's the sky above.
No, so that's the ground floor. So this is a plan view, and then the one on the right is a roof section.
Oh, I'm sorry. Okay.
So they're two different designs, yeah, of 2 different areas.
Oh, yeah, of course. Sorry, yeah, I can see the door now. Just bear with me. Okay, so this is coming through a vertical wall, so that's okay. There's a few things here, and one of the things I was going to talk to you about when we talk about acoustics a bit more is in the Fantech catalogue, and I've got it. I can show you in a minute. There's a section that's called installation do's and don'ts, and I think we might have talked about this with fans, about the way that a fan should be installed and a way a fan should not be installed. Well, it's the same with attenuators. Firstly, so this is a louver, is it, along here?
Yeah.
So that the distance between the louver and the intake to the attenuator should be, let's say, 1 metre. Now, I don't know how much that is, but, and then the orientation of the splitters in the attenuator, because this is a rectangular attenuator, they can be either horizontal or vertical. In this case, they should be vertical because the air's coming through at different levels. So they should be vertical. If it's horizontal, then you're getting some air that wants to go through some splitters and you might starve other splitters. So you get a very high pressure drop and poor attenuation. So that's one thing. The next thing is this, the length of this transition between the attenuator and the fan. That should be a long transition. Now, I know you're probably tight for space here. So this is a really good example of how the attenuators should not be installed. So I'll just talk about what we should do and how can you resolve that. So having a very short transition like that affects the performance of the attenuator, and it also affects the performance of the fan. Likewise, on the outlet side, you've got a very short transition there, which obviously it's very tight space, but then you've got a bend before the attenuator. So that's a no-no as well, because the air coming around the bend is tending to go to the outside of the bend and not the inside of the bend. And so you're starving the attenuator of air again. If you have horizontal splitters in the plane of what we're looking at, then that helps. But there should be a bit of straight duct. So the length of that attenuator should be just straight plain duct before you actually get to the attenuator. So that's a good example of how not to do it. Do you want me to share the do's and don'ts? I mean, you can look them up anyway. In the Fantech catalogue, you just go to the section on, I think it's called installation do's and don'ts, and you'll find what you should and shouldn't do.
So for this particular area, because it's such a debatable design, it's worth sending to a acoustic engineer for analysis, because it's like most likely not correct.
Yeah, I think you might have some issues with this. But what's the what's it supplying to?
So this is the ground
Car park
floor.
supply. Okay.
Yeah. So the ground is taking it from ground floor level louver past. I'm not sure what the rooms are on the left and the right. There's like a substation on the right, and then a water room on the left.
Oh,
And then it's going down to the basement via a cavity in the slab.
right. Okay.
And then it
So is
supplies air.
So is this the cavity below the attenuator here?
Yeah.
So it's blasting out of there, and then it's going to go down a hole in the floor.
Yeah.
Okay. And what's the sound level of that fan? It's doing a lot of air, 8,600 litres. OP 804. So it's 800 diameter 4-pole fan. That'll be fairly noisy. So you've got a couple of issues. One is the noise that's going to the outside, And what's just outside here?
It's just the
Like a podium area, isn't it?
Pathway. It'll be near the. It'll be like a garden, like a lawn area, just in front of the building.
Right. Okay. So may or may not be a problem, but I don't know whether you ever noticed walking past certain buildings. Sometimes you hear a lot of noise coming out of louvers, intake louvers. And I can remember one, there's a really nice hotel in Ballina, which is in the north on the north coast of New South Wales.
Yeah.
And it's got an intake. I don't know what it's for, but you can see the louver on the wall of the building, and the noise coming out of there is just awful. And this is the sort of thing that can happen. Even with an attenuator, the attenuator shown on your drawing there is quite short by the look of it.
Yeah.
And the reason they've gone to a rectangular attenuator instead of a circular one would be because they're trying to get a lot of attenuation, or a fair degree of attenuation, which you can get from rectangular, but you wouldn't get from a circular attenuator. So if you had a circular attenuator, it could bolt straight onto the fan, but you don't get much attenuation from those because it's just like a piece of duct with a bit of lining in it.
Yeah.
A rectangular attenuator has splitters, so the air is absorbed in all those splitters inside the attenuator.
The schedule's here. So this supply fan, the basement one, see here the sound level.
Yeah, so those sound power levels are fairly high. The dBA, the overall sound pressure level, is 69. So yeah, I think you would need to do a calculation on that.
Yeah.
The thing that you can't really get out of the calculation is the effect of bad installation, for want of a better way of putting it, for not installing it the correct way. And if you put an attenuator on a bend or like that one, or with those not in accordance with the recommendations, then that will affect the performance of the attenuator in terms of its sound absorption, and it will affect the fan as well because it creates more turbulence. It's one of those things it would be described in textbooks somewhere, I suppose, but I'm just trying to give you a bit of an idea of the issues you can have. So just go back to your drawing.
Yeah. Do it here. I've got the full drawing here. It's really big.
So the air's blasting out of here, and then it's going to hit that wall and then go down. So it's not ideal.
This is an office space as well, I think. So it's literally like the wall adjoining that.
Yeah, and this bend is not lined.
I think it's probably meant to be, but no, in the drawing it's not.
Okay. Well, I mean, that's something you could do, but as you can see, that attenuator is right on the bend. If you look at the recommendations, they say, well, as I said before, if you could have a straight piece of duct after the bend to the attenuator, that would help the attenuator to do its job a lot better, but then you haven't got space for that. So it's a difficult one. It would certainly need to be looked at carefully, and probably by someone who is a specialist in acoustics.
Yeah.
Because the system effects are the issue. Like you can say this attenuator will give you so much attenuation, line bend will give you so much, this attenuator will give you so much, and the answer is it works. But the system effect, because of all these turbulent elements, it won't work the way you think it will. So is there any, I guess with the space you've got, the space restrictions, there's not much you can do. And unless you change the design in some way.
Yeah.
So I don't know anything about what's going on in the project, so I don't want to say too much, but it definitely needs someone to have a good look at that.
Yeah.
And if you know, if you were discussing it with them, just say, well, and for all of you to have a look at installation do's and don'ts on in the Fantech catalogue, because Fantech's history is very long. When I started work back in 1980, the founding company of Fantech was called Air and Noise Engineering. So these guys were specialists in fans and noise. And that DNA, if you like, has been carried through Fantech, you know, all through the years. So if they're saying this is what you should do or this is what you should not do, then we need to take notice of that and try and achieve the recommended way to install things. I know you can't always do it, but the problem is you can't expect that system to perform to a theoretical calculation when it's going to be installed like that. Does that make sense what I'm saying?
Yeah.
Did you want to, out of interest, do you want to have a look at those do's and don'ts? Or have you got time to look at that?
So I probably haven't got much time myself.
Okay. All right, well, let's just finish off. Did you want to talk about that other section there that you had, or?
Yeah, we're gonna have a quick look at it. The I think the issue here wasn't as complex as this one. So this is basically, yeah, so it's on the roof. And from what I remember through some of the meetings that we had, this attenuator is just going to be taken out. And that's mainly why the air is on hold, just because they don't feel that they need it there. It's just going to be a line duct.
So this is a car park exhaust fan, is it?
Yeah. So it runs from the roof all the way down to the basement.
Right. And you've got, okay, internally lined duct along here and around the bend. And does that go into a riser shaft then?
Yeah, so it stops there, and
Okay.
that's contained shaft.
Yeah, okay. Well, it's an easy one to do a calculation on, I suppose. If the attenuator is required, the location of that looks quite good. You've got a fairly long transition into the fan. There's no attenuators on the discharge side. So the installation looks quite good, but you might internally lining the duct instead of putting an attenuator might do the job in that case.
And what are you protecting by trying to dampen the sound in this situation? I'm guessing it's going to be the apartments below. Because on the roof, there's not anyone on the roof, is there? So it doesn't really matter if it's loud up there.
No, the roof should be okay. Well, you will have sound in the riser. Does the riser have a common wall with apartments?
I'll double check. I don't think so. Can't really tell on that one. actually got the Reddit open. I was looking
I say that because, you know, the noise coming from the fan will be in that riser shaft, and that's like a reverberating chamber going down to the car park. If it's an open shaft, which it is, and that noise can break out of that shaft into apartments potentially.
Yeah, there are apartments around it. So this is the lift here.
Yeah.
See, this is one apartment. It's like the kitchen and the bathroom, both have walls next to it.
Where's the car park riser?
It'll be here.
Oh yeah. Oh, what, behind the lift or?
I think it's in the lift. It's part of the lift shaft.
That would be unusual to do it that way. It should be a separate riser shaft because should be a separate fire compartment. The car park exhaust riser. I was thinking that it might be.
Have a look. Yeah.
I was thinking it might be this area here, but no, it can't be because is at the bathroom.
Oh yeah, it's this area here. So it's next to the stairwell. It's like a gap.
Oh yeah, okay. Which has a common wall to the apartment, but it looks like that's concrete, is it?
Yeah.
Yeah. Also, concrete is a good sound barrier. It's solid formed concrete like that. I don't think that would be an issue in the shaft in that case. So really you're just concerned with whether the noise on the roof is going to be an issue for adjacent buildings, for instance, or
Yeah.
so the noise here, whether that's going to affect, and what's this here?
So you know how on the top of buildings, I don't know what they're called. It's like a louver,
Oh yeah,
acoustic
okay.
louver or something.
But then it's open above that, is it?
Yeah.
Yeah, so they're the things to consider is whether this fan noise might affect an adjacent building or if there's an apartment just below there that has windows, for instance, that might be affected by the noise. And then on the inlet side, whether you're achieving the sound levels required in the car park, but I don't think you'd have an issue with that, excuse me, in this case.
Yeah.
Because you can have up to 65 dBA in a car park, I think it is. So my gut feeling is that with line duct, you'd probably be okay, but it's probably worth doing a quick calculation to check that. Because you don't want to find out at the end of the job that, oh, we're a couple of dB over and they won't accept it. So just check it and get it right before you start.
Yeah. I'm good. But yeah, I think that's pretty much it for me in terms of
Yeah, okay. Well, we'll probably talk mostly about acoustics, which is extremely important. And it relates to the duct design as well, in all cases. Bad duct design will cause noise. So we always want to design ducts in the right way. And there's plenty of information available that tells you the best way to do ductwork and fittings and so on.
yeah.
So we'll talk some more about that probably next week. Will we go into acoustics next week, or Jalen, do you want to share something?
I have nothing to share at the moment.
You're keeping
Yeah,
it all
in
to
fact,
yourself, are you?
no. I'm on pretty menial talk at the moment. So, yeah.
Okay. Well, how about next week we talk a bit more about acoustics then? Or you?
I'd like that. Yeah.
Sounds
Yeah, okay.
good.
Sounds good.
we'll start from the very basics, but we'll dig in a bit deeper as we go along, and I'll talk to you about the note. I've sent you the notes. I've put it down as 2 parts because I think it's too much for one session. But we'll also talk. I'll also talk to you about selecting attenuators if you find that they're necessary. There's a process there, and we'll talk about installation do's and don'ts, which I mentioned a few times today, to be aware of. And this is acoustic. If you have an acoustic problem on a project, they can be difficult to resolve. So having the awareness when you're doing the design and trying to do everything you can to make sure that you're not going to have a problem is going to pay off big time at the end. So, okay.
Yep.
Great. Thanks, guys.
Thanks,
All
Peter.
Later.
Thanks,
See you
George.
next
Peter.
week.
See you guys.
Okay.
So, yeah.
Bye.